Memristors explained, cutting-edge technology with brain-inspired power, low cost, and size efficiency. The currently dominant shared memory von Neumann computers assume two base constraints. 1. Separation of memory and processing units, connected via increasingly complex bus and caching structures. And 2. Quantized, digital, shared memory for both instructions and data values. The simple compact structure of memristors and the uniform processing structure of neural networks enable architectures that relax both of these constraints. Removal of the first constraint will provide orders of magnitude improvement in power consumption, processing speed, and cost. These improvements, in turn, enable real-time, continuous, in-situ updating, online learning that is missing in current systems. Such online learning may benefit from relaxation of the second constraint using non-quantized analog data values. How does the analog control of a memristor function? Analog control of a memristor refers to the ability to adjust its resistance in a continuous, analog manner rather than discrete steps. This means the memristor's resistance can be fine-tuned to any value within a range, providing smooth and precise control over its electrical properties. In practical terms, analog control enables the memristor to mimic the way biological synapses work in the brain, where signals are transmitted and processed with varying intensity. This capability is especially useful in applications like neuromorphic computing and machine learning, where gradual changes in weight or resistance allow for more refined adjustments during learning processes, leading to greater accuracy and efficiency. Here's a breakdown of what analog control achieves in memristors. 1. Smooth adjustability. Instead of switching between fixed states, like on-off, analog-controlled memristors can represent a spectrum of resistance values. This is key for representing subtle data variations and enhancing memory retention. 2. Enhanced precision. The continuous adjustment of resistance allows for precise weight tuning in neural network applications, which can improve learning and adaptability in AI systems. 3. Energy efficiency. Analog control often allows for lower power operation since small changes in resistance don't require the abrupt current shifts seen in digital binary devices. Number 4. Neuromorphic applications. Analog memristors can closely mimic the strength and decay of biological synapses, making them ideal for applications in brain-inspired computing. In summary, analog control offers finer, real-time control over the memristor's properties, paving the way for advanced applications in fields requiring high precision and adaptability. How to access data stored on an analog-controlled memristor? Accessing data stored on an analog-controlled memristor typically involves reading the resistance state of the device. Here's how data retrieval works for a memristor in analog mode. 1. Resistance measurement. Since the information in an analog memristor is stored as varying resistance levels, retrieving data requires measuring the memristor's current resistance state. This is done by applying a low read voltage across the memristor, which avoids disturbing or altering its stored value. 2. Analog to digital conversion. The read current or voltage response from the memristor, proportional to its resistance, is detected and often converted from an analog value into a digital format. This digital value represents the resistance level and, by extension, the data stored on the device. 3. Interpreting data. The analog resistance state can represent a continuum of values, allowing for more nuanced information storage. Depending on the application, these resistance levels can correspond to different weights in neural networks, variable data points, or even grayscale image intensities, depending on the resolution of the readout circuitry. 4. Non-destructive reading. Because analog memristors can hold a range of resistance values rather than just on or off, the read process needs to be carefully managed to avoid disturbing these fine-tuned resistance levels. Thus, read operations usually involve a very low voltage pulse to ensure non-destructive access to the stored data. 5. Data interpretation and usage. In neuromorphic and AI applications, each memristor's resistance state can represent a synaptic weight, and by reading these weights across a memristor array, the system retrieves the trained parameters for computations. In other contexts, resistance levels can store analog values directly used by applications that interpret varying data levels. Accessing data in this analog-controlled manner provides a way to retrieve more than just binary information, making memristors suitable for applications requiring fine gradients of information.